Welcome back. We will be looking at mixed partials and repeated partials now. Let's let z be equal to f of xy. We define the so this symbol here is read in the in this way. This is the second partial derivative of f with respect to x twice. That is, it is also denoted by fxx, and it is also denoted by the second partial derivative of z with respect to x twice. Another notation for another, so these are all the same, all of them denote the same thing. So this is d1f, and so all of them are basically the following. You take the partial derivative of f with respect to x, whatever is obtained, you take the partial derivative of that with respect to x again, right? So all of these symbols, they mean this. Similarly for the second partial derivative of f with respect to y. Now the first two, those are the repeated partials, and here we have the mixed partials. So this is the second partial derivative of f with respect to x and then with respect to y. We can also denote that by, because we are using z to denote f of xy, we can also write second partial derivative of z with respect to x and then y. This is also denoted by fxy. So you take the partial derivative of f with respect to x and then with respect to y. We can also write d2 d1f. So that is, we take the derivative of f with respect to the first coordinate x and then with respect to the second coordinate y. And we can also write this. This is you take the partial derivative of f with respect to x first, and then whatever is obtained, we take the derivative of that with respect to y. So those are the second partial. So this is a second partial derivative of f. This is the second partial derivative of f with respect to x and then y. Now, similarly, we can define the second partial derivative of f with respect to y first and then with respect to x. The higher order partials are defined for functions of three variables in a similar way. I have a typo here. I shouldn't be using z to denote the function when z is a variable. So here I should be writing w. Okay, so let's do the following example. Let's say z is x cubed plus x squared y cubed minus 2y squared. Let's find the mixed partial derivatives of z with respect to x and y. So what is zxy? Well, that's the partial derivative of z with respect to x first and then with respect to y. So let's take the derivative of z with respect to x first. With respect to x, y is a fixed constant. So with respect to x, the derivative of x cubed is 3x squared. With respect to x, the derivative of x squared y cubed would be y cubed multiplied by the derivative of x squared, which is 2x. So we get 2xy cubed. And the derivative of 2y squared with respect to x would be 0. So then now we have to take the partial derivative of this with respect to y. Now with respect to y, x is a fixed constant. So the derivative of 3x squared would be 0, and the derivative of 2xy cubed with respect to y would be 2x times the derivative of y cubed, which would be 3y squared. So we get 2x 3y squared, which would be 6xy squared. Now the partial derivative of the mixed partial zyx, that's the partial derivative of z with respect to y first and then with respect to x. So the partial derivative of z with respect to y first would be would be the following. So the derivative of x cubed with respect to y would be 0. Derivative of the middle term here with respect to y would be 3x squared y squared, and the derivative of this guy would be 4y. Now we have to take the derivative of this with respect to x. With respect to x, we get 6xy squared, and the derivative of 4y would be 0, so we get 6xy squared. So notice that zxy and zyx are the same. Let's say that f of xyz is equal to sine of 3x plus yz, and we want to find the mixed partial fxxyz. So this is, so you have to be, so when we are reading this the subscripts here or the indices here, this is you are taking the derivative of f with respect to x first, and then with respect to x again, then with respect to y, and then with respect to z. So we're taking derivative 4 times. So first we find the partial derivative of f with respect to x. So with respect to x, y and z are fixed, so we get cosine of 3x plus yz, and then the derivative of this inside here with respect to x would be 3. So we get 3 cosine 3x plus yz. Now we take the derivative of this now with respect to x again. So now it'll be 3 times the derivative of cosine 3x plus yz with respect to x. Now derivative of cosine would be negative sine. So negative sine evaluated at 3x plus yz. And then we have to multiply by the derivative of 3x plus yz, which is going to be 3 again. We already had a 3 here. Another 3 would give us a 9. So that's how we're getting negative 9. So here what I'm trying to say is when I take the derivative of fx with respect to x again, we get 3, and then negative sine of 3x plus yz, and then we have to multiply by the derivative of the inside, which is 3 with respect to x. So we're going to get negative 9 sine of 3x plus yz. So now we take the derivative of fxx with respect to y. Now with respect to y, x and z are fixed. So the derivative would be negative 9. So now I'm taking with respect to y. So I'm going to get negative 9. And then derivative of sine is cosine evaluated at 3x plus yz. And then we multiply by the derivative of derivative with respect to y of 3x plus yz. And with respect to y, x is fixed, so the derivative of 3x would be 0. And the derivative of yz with respect to y would be z. So that's why we're getting negative 9z cosine of 3x plus yz. Now, finally, we take the derivative of fxxy with respect to z. With respect to z, again, x and y are fixed. So now, notice that we have to apply the product rule, because now minus 9z is a factor in the function, and cosine of 3x plus yz is another factor. So we have 2 factors each, where each one of them is a function of z. So by the product rule, we take the derivative of negative 9z, which is negative 9, multiplied by the second factor as it is, plus the first factor negative 9z, multiplied by, so negative 9z here would be multiplied by the derivative of this guy with respect to z, which would be negative sine of 3x plus yz, and then multiplied by the derivative of 3x plus yz with respect to z, and which would be y. So if we clean up a little bit, we get negative 9 cosine of 3x plus yz plus 9yz sine of 3x plus yz. Let me state a theorem. So in one of this in this example that we have just done, we saw that zxy and zyx were the same. That is, the partial derivative of z with respect to x and then with respect to y is the same as the partial derivative of z with respect to y then with respect to x. So this is not a coincidence, in fact. So if I have a function f of two variables x and y, and let's say it is defined in an open disk D centered at the point AB, if the partial derivatives of f, so this is the partial derivative of f with respect to x, partial derivative of f with respect to y, and the mixed partials of f, if all these partials are defined and are continuous at the point AB, then it turns out that these two mixed partials are the same at AB. So this theorem is pretty much explaining the conditions under which these mixed partials are the same. So here, the mixed partials that we are getting, they are the partial derivatives and the mixed partial derivatives, they are all continuous, and that's why they are, the mixed partials are supposed to be the same. Okay, so let me end by the following. This equation that the second partial derivative of u with respect to x twice plus the second partial derivative of u with respect to y twice is equal to 0. So this is known as the Laplace equation, and the question is asking to show that u equal to e to the x times sine y is a solution to this Laplace equation. Solutions of the Laplace equation are called harmonic functions. So basically we are trying to show that this function here is a harmonic function. All right, to show that e to the x sine y satisfies the Laplace equation, we basically have to calculate the second partial derivatives of this function and then plug them in here and see if we get 0. Okay, what's the partial derivative of u with respect to x? Well, with respect to x, sine y would be a constant, so it will get e to the x times sine y. What's the second partial derivative of u with respect to x? Twice again, so that's going to be taking the derivative of this guy with respect to x again, we get e to the x sine y again. Okay, what's the partial derivative of e to the x sine y with respect to y? Well, with respect to y, e to the x is a fixed constant, so we get e to the x multiplied by the derivative of sine y with respect to y, which would be cosine y. Now we take the derivative of this with respect to y again, and then we get e to the x times the derivative of cosine of y, which is negative sine y. So this is what we get. So now if I add the second partial derivatives of u with respect to x plus the second partial derivative of u with respect to y, if we add them, we see that we get 0. So indeed the function e to the x, e to the x sine y satisfies the Laplace equation, and therefore it is a harmonic function. Okay, let me end here. In the next video, we will be looking at gradients.